Hello, I am Avery Campbell, and I am joined by Clayton Tobin, Bradley Doman, Gavin McIntosh of the TSU Particle Modeling Group. Today we will be presenting our simulations to demonstrate the harmonies amongst two stars. What is a binary star? Binary stars are stellar systems that contain two stars orbiting a barycenter, also called the center of mass. Binary stars are typically arranged in three configurations: detached, semi-detached, and contact. A contact binary system is where two stars exchange masses, and in general, this idea can vary drastically different classifications. A few examples of this would be a neutron star, dwarf star, or even a black hole. Semi-detached binary is where one of the two stars fill the Roche load, but do not touch each other, meaning the mass of one of the stars is pulling in some of the mass of the other star, where the mass can generally remain at a proximity, but as time passes, the same mass of gas can form an accretion disk around the pulling star. And finally, a detached binary star system is where the two stars remain without contact, and either one's gravitational pull is not significant enough in order for it to be classified as a semi-detached. These are relatively passive star systems where the two can orbit and grow without either one getting in their way. These stars can come in all different shapes or sizes. Our simulation is able to run with an infinite variation of orbits, along with the ability to vary the star's and core's diameter and mass, in addition to the direction of its initial spin and angular velocity. With this, we can simulate any star's orbital patterns and their classifications. Up next, Gavin will present an example of our computerized model of a binary system.
Thank you, Avery. Today I will be showing you behind the scenes of how we simulate binary star systems in the Tarleton High Performance Computer Lab. Here we use NVIDIA graphics cards to handle the staggering amounts of calculations required by our binary star simulations. With each simulation, we have to calculate the position of each individual particle's gravitational pull against every other particle's gravitational pull. The simulation I'm going to present consists of 262,144 particles, which requires over 69 trillion calculations per frame in the video. And these calculations aren't just simple arithmetic. They are complex dynamical equations that we have to implement into our CUDA program. CUDA is a programming language that speaks directly to our NVIDIA GPUs, allowing computations to be completed in parallel. Now, when working with these equations, things don't always come out perfectly. In this simulation here, we have some drastic results. As you can see, the cores of the stars are bouncing together violently and then throwing each other apart, spewing out massive amounts of particles along the way. We ended up finding out that this was an error in our physics calculations, and we needed to go in and fix that. Now that we had fixed the errors in our calculations, this is what it ended up looking like. Now, while it might not be as wild and cool as the other one, this is much more realistic, and we are more likely to see this in the real world. In this specific simulation, there are just two stagnant stars slamming into each other. None of them are changing, and both are exactly the same. This is far from the only situation that could happen in the real world. I'll leave it to Bradley to explain the different types of situations we could run into.
Hello, my name is Bradley Doman. For you today, we have a program where we've created a simulation of a white dwarf and a main sequence, which will have the same parameters as our sun. That sun evolving into a red giant. As you can see here, the very small pixel is the white dwarf. That white dwarf is becoming the core as the red giant is evolving and slowly having its mass be collected by the white dwarf. In turn, it will continue to spin and collect the leftover particles. It will continue spinning and spinning until the core starts to create its final star shape.
Hi, my name is Clayton Tobin, and I'm going to tell you about some of our future work. One of the things we'd like to do is develop a 3D viewer to get a better view of the binary star systems in action. This will allow us to diagnose problems and correct them, and also get more accurate videos of our simulations. Here we have an example of a viewer that we have been building. This viewer will allow us to move around in 3D and get multiple views of our simulation. Here you have an example of our simulation from the side, and you can see the egg shape in the middle, which is our star. This viewer also allows us to move forward and backward in time so we can better view our binary systems. Another thing we'd also like to do is upgrade our NVIDIA GPUs to the new 3090s so we can handle more particles at a time. Thank you for your time.
Just like any two odd masses revolving in the entropic void of space, you never know what the outcome will be. We would like to thank NVIDIA as well as the Tarleton Math Department's High Performance Computing Lab for making this project possible. Thank you for your time, and I hope you learned something new about binary stars.